Right. Good afternoon, everyone. Let's continue where we started, where we stopped last time. Okay, let's get a little bit more quiet. First of all, today we have a special guest, Professor Haitao Wang will observe the lecture and report back to the school. Is everything looking all right here? For us, it's business as usual. Don't change your behavior in any way. So last time we were talking about this groundbreaking idea of pre-training and fine-tuning, right? We have pre-training as a way to prepare the weights of our transformer-based model, whatever we type to choose, encoder only, decoder only, encoder, decoder. And we have used language modeling or mask language modeling to find weights of the transformer that will already capture a lot of linguistic phenomena and be a great starting point for many, many applications that we might be interested in later. And later we are going to just use sort of standard supervised deep learning, meaning we will have some label data and we are going to use negative log likelihood training to change the weights even further to specialize them for the application we have in mind. I promise you next time we were actually going to start looking into applications like question answering, this time for real. So today we are just going to finish with just a few more things that we need to know to kind of fully understand this paradigm. Remember last time we had kind of talked about how to do this along 3 dimensions. What is the transformer time? What is the pre-training objective? And then later, what kind of fine-tuning head, LM or classification head I'm going to use. And this kind of brought us to this tree or a landscape of various pre-trained language models from encoder only to decoder only that we typically use today. Now, I sent you over Piazza a little notebook where I kind of went over this in a slightly different way than I did in the lecture. I shared a stripped down pseudocode for you to kind of see how, what makes a decoder only model with an LM head and how would you use it for conditional text generation. I felt like after the lecture that part didn't really come across, and I understand it's a bit confusing because with encoder decoder, it's really clear where you encode, and it's really clear that the decoder is conditioned on the encoder. And I understand that the first time you see decoder only, a sense of how do we condition might be lost, right? So I hope the pseudocode helped you a little bit. There are no quizzes in this course, as we know, but we will have a little ungraded quiz just to see whether we are, fully landed on understanding that. So you can copy this link. This first link is just the notebook I shared over Piazza. So in case you missed the announcement, I highly encourage you to check that notebook offline to kind of go over the materials in a slightly different format. There is nothing new there, except it's a different format. And let's go over this. You can use your phone or you can use the laptop, whatever you prefer. There is a QR code in the upper right, there's a link on the left. Do you see that? It's a little bit small. I can zoom it probably. Yeah, let me know if you don't see well. It seems like again, this is ungraded. I just want to see whether we have understood that last lecture. And I'll set the timer to 6 minutes. There are 6 questions, I think. Shouldn't need more than a minute per question.
Okay, let's stop here. We need to get going. I'm gonna lock it and let's see what our responses are. Okay, so the first question was about what is the primary difference between encoder-only and decoder-only transformers. And most of you have selected the differences between the self-attention, the bidirectional one, and the causal or mask attention, which is the correct answer. So here, I kind of, if you see, well, it's a little bit tiny here. This is encoder-only transformer, and this is decoder-only transformer. If you really put them side by side, you can see that the only difference is that here it's written masked and here self-attention, right? So that's one thing to kind of, maybe we didn't really emphasize last time, but you should fully embrace, especially for your assignment, as you will see.
I have seen a few of you have selected the third option. Remember that once we have dropped encoder or decoder, there is no concept of cross-attention anymore, right? Cross-attention goes from decoder to encoder, and that's impossible to have if you don't have the encoder, right, or the decoder. Okay, moving on. The second question was, you need to build a system that generates creative stories and also classifies the sentiment of reviews. You must use some pre-trained model for fine-tuning runs. And I ask you to choose the characteristics of the backbone model that's better for this situation, either decoder only model that's pre-trained with language modeling or encoder only that's pre-trained with mask. Does anyone want to explain why they chose first option? Many of you have chosen it, so there are a lot of candidates.
Yeah, from my understanding, the decoder only is, or I guess the encoder is an outputting layer where we can do like an argmax or something like that, where we can get an output token, versus the decoder, we are getting an output layer where we can predict a next token. And so then we can add another head on that as well for the second part where we do the classification.
Yeah, so let me just, you're almost there. There is just a slight, I would say, imprecision there. So in both cases, in both encoder and decoder only transformer, when we pre-train them, we will have output layer that's going to produce the distribution over the lookup, right? And nothing stops us from having argmax or one or the other, right? So the concept of argmax can exist in either case, right? But what you did say, right, is that with decoder-only models, if we use language modeling, we are predicting the next token, right? So we can reuse that LM head to do this task of creative writing. At the same time, I can make a new instance of this decoder-only model, and I can replace the LM head with the classification head and fine-tune it for the classification task, right? So in a system where I have chosen the same decoder-only model, pre-trained with language modeling objective, I can use this model to do two different fine-tuning runs, one for the sentiment classification with classification head, even with the language modeling head if I like, and another run where I fine-tune it for creative writing with the fine-tuning of the LM head. Now, does anyone want to tell me why can't I do that with the encoder-only model that's pre-trained with mask language modeling? Maybe to make the question easier, which of these two tasks becomes harder? Yeah, choose.
You can't do any generation.
Yeah, that's right. So with the encoder-only model that's pre-trained with mask language modeling, we cannot do creative text generation. We can't produce longer pieces of text. And the reason is because the mask language modeling was trained to predict what the next, what the mask token is, not what the next token is. You could challenge me and say, well, what if I end every incomplete part of the text with mask token, and then isn't that the same thing as predicting the next token, right? If the mask token is always at the end of the sentence. And the reason why this won't work is because your pre-training wasn't done where the mask token is always at the end of the sentence, rather somewhere randomly. So it will be a very suboptimal, probably very buggy text generator. Yeah.
I still don't understand how in the decoder, I mean, I understand how the decoder only model can do generation. That's pretty evident. I don't see how it can do a classification task though. I thought the encoder only was what we do if we want to do classification.
No, so I never said that encoder only is the only option for the classification. I said that's a good option, classification. But we have talked extensively about how, first of all, you can use the language modeling head to generate the label, such as positive or negative, right? So you turn your classification task into next token prediction task. That's one option. Another option with decoder-only model is to introduce a new classification head and ignore your LM head. The same way we've done it with decoder only model. And you can fine tune your pre-trained decoder only model with the new classification head, and classification head will be pre-trained, will be fine-tuned from scratch.
But in this question, it's saying you must use the same pre-trained model for fine tuning run, so we'd have to use the LM head for the classification though, right? You must use the same.
No. I mean, it's slight linguistic nuance here. I said, first of all, a system. I didn't say you use one model, right? So I said there is a system, and I said you have runs, fine-tuning runs, not a single fine-tuning run. So I think what is confusing here is the language of this question rather than the actual code. So let's talk offline, but I think you understand everything, and it's just the interpretation of this question is what confused you. But yeah, let's chat after. Okay, next question was, oops. Oh, that was the next question. So you add a classification head to a pre-trained encoder only model. Where does this head typically receive its input from? Who wants to explain their answer? It's okay. There is a variety here, so you shouldn't feel bad about any option you have chosen. I was told if I wait long enough, someone will say something. Oh,
Sure.
yeah.
Well, it's encoder only, so it's not gonna be the first one because we're not getting. Or we're not getting out of messing with one, I don't think. So
What did you choose?
I chose the second.
Second option, and why did you choose it?
It could also be the last one, I think, since we talked about that last time, but it's common practice to use the CLS token.
Yes.
It has self-attention to every other.
Yeah, exactly. So you're right that the last token could also be used here. I did say typically, right? So and you are right that we would use the representation of the CLS token. Remember, we put CLS token as the first token in the input, so we are taking the final representation of the first token in the input as a representation of the entire input to be classified with our classification head. You're right that we could have used the last token because due to self-attention, it's also attending to everything else. But typically, we have introduced CLS token especially for this purpose. We wouldn't use mass token because classification head means you're going to do classification class. You're going to take your input, you're going to classify it into, let's say, positive or negative sum, right? It's not a task of mask language modeling. Therefore, there is no reason for you to choose the representation of a mask. We will take the representation of a mask token only when we do the task of mask language modeling during pretraining. So if you have chosen the last option, in theory, you're not really wrong. But remember that I have said typically here, and that we have introduced CLS token to be used as for this purpose. If I have asked you this question, but I swapped encoder only with decoder only, what option would you choose? Yeah.
Final representation of the last.
Yeah, right. And do you feel like you are confident explaining why?
Yeah, it's because of the masked causal attention that's used in the decoder only. That last token is what's going to be receiving all the information from the prior tokens, whereas the ones that come before, because of the mask, they're not getting all the information.
Exactly right. So I don't have anything to add to this. This is a perfect explanation. Let's move on. In decoder-only transformer for translation, source and targets are concatenated into translate column hello world zdravo svijete. How does the target zdravo attend to the source token? Which mechanism allows you this? And now maybe even if you have chosen whatever else other option, through this discussion we are having so far, you would come to the answer through causal attention, right? So in decoder-only model, the position zdravo, we can attend to previous tokens through the causal attention. Cross attention, again, this is more like a distractor option. Again, we don't have cross attention in decoder only or encoder only model. So again, if you had forgotten that, please remember that cross attention exists only in encoder decoder transformer. And then the last option, also remember that we can do conditional text generation with decoder only models. And as we are going to see, as we progress with the course, large language models like ChatGPT, which are all about conditional text generation, given your prompt, they give you responses, are decoder only models. So it's really important that you remember that although it was really easy to embrace conditional text generation with encoder decoder transformer as it was introduced in 2017, today we use decoder only models, and they can certainly do conditional text generation. Okay, next question was training a decoder only with input translate hello world zdravo svijete, which positions contribute to the loss? So if you have reviewed the notebook that I shared over Piazza yesterday or the day before, then this probably was easier question. Does anyone feel comfortable answering this question? This is probably a trickier one. Okay, let me explain it. So in this is again conditional text generation, right? The task is machine translation. We have a source sentence which is translate column hello world, and we have the target sequence which is zdravo svijete. The goal is to produce the target sequence, right? Zdravo svijete. The goal isn't to produce the source sequence, so we should not be trying to do that, and we should not be calculating the loss over the predicting the source tokens, right? So that's our first conceptual thing to realize. If we are using decoder only model, we are going to place our source into the model the same way we would target tokens. And I think that's a little bit hard to kind of really embrace. So although your source tokens are going to go through this step decoder, and you are going to get the representation for each source token, which you need to actually be able to do the causal attention later on the target positions, you don't care what the model thinks the next token would be at the first source token position. You know what the source token is and will kind of stick with it, right? So calculating loss there is irrelevant. So all input positions wasn't the right answer here, right? Because we are not calculating the loss over the source tokens, almost all except the last source token. Last source token is world, and this is a position where we need to start generating the next target. So when we put our token world, it's going to go through the decoder step. We will have causal attention to translate column hello and so on. We are going to get to the final representation of world, and at that point we have our LM head, and with our LM head we get the logits and then probability over the VUCA, and we can use that probability to calculate the negative log like, right? We know what the next token should be. It should be zdravo. So we are checking what is the probability of token zdravo under our softmax vector, and we apply logarithm negated, and that's our negative log likelihood loss, right? And we are going to use it. So we are going to use it at position world, at position zdravo, where we are trying to predict svijete, and at position svijete, we are also going to need to predict that last special token and the sequence token. And that's it. Those are the positions where we are actually calculating the loss. Final position wasn't the right answer because at the final position, we get only the loss of predicting the last generated token, not the entire sequence, right? We need losses over world zdravo svijete, and we are going to average those. That's going to be average loss that we are going to use to back. Yes, please.
So if I'm understanding this correctly, when we're considering the loss, we basically want to consider the position of the final source token and then all the target tokens afterwards. So since world is the final source, that's where we start and then we do the loss parameters.
Except the last, I didn't add it here, but that's my
Except the
end of sequence. Yeah. At that point, you should start just if you keep prompting the model to generate stuff, it should just generate end of sequence token, but we don't really care about this. Yeah.
So if we were retraining the model, then the first answer would be the right one, because we're just trying to teach it language model. It's only for fine tuning specifically for translation of the second options.
Yeah, you're right. So you would start with the beginning of sequence token, and then it would predict something. And this is such a silly concept because, like, what is the right way to start a sentence? So I think at the beginning of pre-training, at the beginning of your sequences, you will always have higher loss than you have at the, later stages, because it's just, at some point the model will figure out what are the typical ways people do start sentences, but there are so many ways, right? So if you're thinking, yes, loss is going to be higher there, for sure, it will be. Yeah. Okay, if this was not tricky and it's still tricky to understand, please check out Colab that I have shared with you. This should really be, I think, super clear from, I have given you an example, I have showed you how we calculate loss in 2 different ways, so it should be really, really clear from there. Okay, and the final one is just yet another way to try and see whether we are okay with teacher forcing. So it asks, we are using teacher forcing, the model predicts bonjour, but the target is salut. And what gets fed as the next input token, most of you have chosen salut, which is the right option here, right? With teacher forcing, regardless of what the model thinks the next word is, during training, when we use teacher forcing, we use what's in the actual data. And we use that to speed up training, because then we don't need to sample the word to, extend our input. Rather, we can immediately construct a batch of inputs, get the losses, causal attention, make sure that we are not doing any cheating. And we get, with a single forward pass, we get losses over all target positions, instead of doing this as a for loop and then multiple times, which is also clear if you check the notebook. Okay, so let's stop here with the quiz. That's its end. I hope things are a little bit clearer now with these various options. Check this Colab, and I think it certainly will be. Give me just a second to make sure that now I'm sharing the screen and not my face, which I should be doing, but you know what? Like, whenever I see here myself instead of this the slides, I feel like it's not recording the slides. Do you know whether that's the case? Not really. Let me just play around, otherwise the recording is going to be messed up a little bit. Do you know? No, you don't. It seems like you're one to suggest something. Sorry about that. I'm desperate. I'm like, every reaction is like, the answer. Oh, okay. It seems it's like, oh no, this is mirroring. Okay, give me a second to debug this. I mean, it should be. Okay, I say stop sharing. And then I share the poll.
Yeah, you're sharing the web page now. See how
Yeah.
there's that green outline?
Yeah, but look at this. So right now, if I go over here, oh no, it's also my face.
I wouldn't worry about that.
You wouldn't worry. Okay, then I will cite you when you're recording this. Okay, let's hope for the best. All right, so let me also show you a little bit of Hugging Face stuff. So remember how I keep saying that the Hugging Face is an ecosystem, libraries they include from transformers, tokenizers, data sets are the state-of-the-art libraries to use if you are working with pre-trained models, from language models to vision language models to audio language models, any kind of open source AI stuff is happening with Hugging Face. If this was a smaller course, we would have projects, and you would certainly be tasked to use some of these libraries to produce something. There is not something we can handle in this course, but it doesn't mean it's not important. I really welcome you, if you are interested to kind of, work in this space, to try some of this stuff yourself. This is basically what you would end up doing in research, or if you turn out to be an engineer or data scientist. So first resource I want to point you to is this Hugging Faces notebooks. Here you have so many wonderful resources on how to use their libraries to do all sorts of things. So here you see you have how to fine-tune a model for text classification, how to fine-tune a model on language modeling, and so on. So if you are interested in how to actually do this and use the library that everyone is using to do these tasks, please check these notebooks. They are written in a really, really nice way. So for example, here, I will just scroll through one of them. The one and this one. Okay, so for example, here you have how to fine-tune a model on text classification. And they're using a task, not a task, but a collection of tasks called Glue. If you remember last time I told you that Glue was this benchmark everyone was using at the time to kind of say who has a better model. Right now, it's completely outdated. It's not something we would use, but here you have your sentiment classification task you have been using in your first two assignments. Okay, so the notebook will show you how you can load a data set with Hugging Face, which you should check out. And you did play around a little bit with it in the practicum, where I forced you to load a wiki text, right, with the Hugging Face's data sets. So they do that, they pre-process the data. So now here as a first step of pre-processing, we always have tokenization, right? We never can escape tokenization. Now, they are using a tokenizer from a specific model. Do we remember a connection between a tokenizer and a model? Why can't we use any tokenizer with any model? What's the connection? Yes, please.
They have to match the dimensionality.
Tokenizer doesn't have a dimensionality. What do you mean by your
I think I got it back. Maybe something else.
Okay, say something else. Okay.
Some of the model has like certain, like it has an embedding for each token in the vocabulary. And then also if you're doing like text generation, then it has like the max output for each token in the vocabulary. And so if you use a different tokenizer, then you get a token that's not in the vocabulary.
Yeah, exactly. So our embedding metrics and our so-called unembedding layer, where we do predictions into the vocabulary, they are constructed by knowing what's in the vocabulary, right? So my first row in embedding metrics, I think question asked with brilliant science by this point, right, is going to be the embedding of a token with the vocab ID 0, right? Not of any other token. So if I have a vocabulary whose I don't know, first token in the vocab is a cat, in another one is dog, then I completely miss the mapping. And of course, the tokens themselves are going to change depending on what the tokenizer does, because we are using the subword tokenization that learns tokens from the data, right? So it's crucial that you are always using the tokenizer that was created for the same model you want to use. And what's nice with Hugging Face is that you really don't need to think about this low-level details. So they have these auto classes, right? So you load from auto tokenizer, and then from auto tokenizer class, you are looking for a tokenizer that's connected to a model with certain name, which you get here. This is a variable model checkpoint, but you would give an actual name like bird or the bird You don't need to pay attention to the actual name, so let me show you. So I go to huggingface.co and I search for BERT. This is the BERT model. So here, BERT based uncased, you typically just click copy here, and that's the model name you are going to place here under model checkpoint. Okay, so you need to pay attention to that. Otherwise, if you miss the name, it won't find the right thing for you. Okay, so you need to do that to get the tokenizer for the model you care about, and then you can tokenize these sentences. One nice thing about Hugging Face is that it has this map function. So you can create a pre-processing function such as tokenize, and if you use dataset.map, it's going to apply this processing function to every element of your dataset. So you don't need to write those for loops and extra code to achieve things like that. It's written already for you. Okay, so that's about pre-processing. You now turn to fine-tuning a model. Here we get that auto model for sequence classification I was making some fuss about last night, if you remember. So again, because we're using these auto classes, this code for that takes the weights of a Pretraining model, kind of overrides whatever random weights and constructs a classification head which is randomly initialized. None of that is something you need to write. All you need to know is that, all right, I want to do sequence classification, so I'm going to use a class auto model for sequence classification. And then I'm going to use a function from pretrained, which is going to load the weights of the pretrained model I care about, and it's going to also construct the classification head for me and randomly initialize it. Once you have that, you need to define a trainer class. Trainer class will have trainer arguments. This is where basically you record hyperparameters that I don't know where you exactly recorded in your homework, but here you would have, for example, learning rate will be part of the training arguments. Training arguments class is also loaded from the transformers library, okay, and the trainer class. Once you have your trainer arguments, then you're going to construct an instance of a trainer class where you are going to give these arguments together with the data. And then your training loop boils down to trainer.train. Super simple, right? So you have to create an instance of a training arguments class, instance of a trainer class. But once you have all of that, you just call train, and training will be done for you. After training, you can also do evaluate, and it's going to do evaluation on the dev set. However, very often you actually want to load the model after the training and do the evaluation without repeating the training, and just the evaluation. And here you can see how you can do that or not. I will share code for that I have. So I don't remember exactly, but I think if you use something like the Berta version 3 model large, you can get with the running notebook like this accuracy of 90-something%. Do you remember how it was your accuracy in your first assignments, roughly? 75. Yeah. 75, right? So if I'm right, you would get certainly something like 90 here. So you get this 15% accuracy increase just by using a pre-trained transformer-based model and fine-tune on your data. So as we start to talk about applications, we are going to return to these notebooks and see what kinds of bits and pieces need to change. But this kind of code is something you would use to this day. Like my PhD research students, they are going to do something like that if they want to fine-tune a model. And if they want to prompt a model, meaning we don't do any fine-tuning, it's going to be even simpler. Now, these Colabs notebooks, they have some GPU, right? But those GPUs are not super powerful, meaning that their memory isn't really big. Meaning that you can't put really large models on those GPUs, and also you're bounded by their availability by Colab folks. So what would be more professional to do is to use servers, right? We are lucky to have really, really good GPU service here at the University of Utah. If you haven't heard, CHPC, Center for High Performance Computing, is where our GPUs are. And I have shared a link to how you can make an account and access those GPUs. If you are a student in Faulkner School of Computing, you can have an account without being in a class which has class token or without being advised by a PI who needs to approve your account. And you can access partitions called SOC-NP-GPU, or sorry, SOC-NP, SOC-GPU-NP. Every School of Computing student can access those. Those are, you will be in a queue where everyone else is, so you might be waiting a little bit longer, but typically not too long. And the GPUs we have there range from 40 gigabytes, 80 gigabytes, to even 100-something gigabytes of GPU memory, which are really, really, really good GPUs. So you can run really large models, and especially later in the course, I will teach you how can you quantize models and how can you fine-tune quantized models, meaning they are going to have less memory to store them without losing performance. So you can do quite a lot on CHPC. So again, this course won't have a project component where I force you to actually do this. But I did left my CHPC instructions for the courses where I did force students to do this. So you can check those out. And if you're interested to really run code on GPU as a researcher would, or later as a data scientist, I really, really encourage you to try these things out for yourself. Okay, so now, last thing we need to go over before we actually turn to more applications. And then after we are done with some applications, we're going to talk about instruction fine-tuning and alignment, which are what is going to make large language models. Before we go into all of that, we need to talk a little bit more about pre-trained data, because knowing what's in the pre-training data is important to understanding what can we do later on. Are there any questions before we proceed with the pre-training data? Would you like a little break? Nope. Okay, let's get into it then. So before I teach, when I teach pre-training data, I love to bring up this tweet by a researcher who studies pre-training data, where he said that, you know, it's basically mysticism how we do this. There is no public, very little data is actually, pre-training data is publicly released, and guidelines for how pre-training data is actually constructed is mostly guided by what he says, intuition, rumors, and partial information. The reason for this is because of these companies that are creating pre-trained models. The pre-training data is something like a secret sauce, right? So you can't give away what kind of pre-training data you have used. It is also invitation for a lot of lawsuits, as we are going to talk about really soon. So there is, however, a resource called DOLMA. That's a pre-training corpus that was released by Allen Institute for AI, whose mission is to release everything from code to data to weight of pre-trained language models. So they have released DOLMA, which is the pre-training data they use to pre-train a model called OLMA. And they have documented it pretty well. So this kind of gives us a sense of what everyone else is doing, because, you know, it's not the case that this is, you know, that some other company has something so extra special and different from everyone else. Everyone is using what's basically available. So here in this table, in every row, you can see where the source of the data is. Then we can see what type that data has, together with information about basically a size of that data within the whole pre-trained data set. First thing you can notice is that a vast majority of this data come from web, from Common Crawl. So people take the snapshots of the internet that are available on Common Crawl and compile pre-training data out of them. Then you can see a lot of data comes from GitHub. And we know that GitHub isn't really just text. It's a lot of code, right? Predominantly code. So it's also important to remember that in pre-training corpus, we have not only natural language, but very often code data. And this is where these capabilities of LLMs to do code can come from, right? It comes from the huge availability of code data on GitHub. We have a lot of social media posts like Reddit, and then we have a small fraction of what we call high quality data. There's going to be academic papers that are available on Semantic Scholar, the permissive licenses like CC BY and MIT archive license. I'm not actually sure for archive license. I think they had made fuss about that. So CC BY and MIT. We have books already should be a little bit concerning there, right? Like some books maybe are copyrighted, maybe not. And then we have Wikipedia, which is also deemed to be highly high quality resource. Typically, we don't have like a full-on spam on Wikipedia. What do we think about web pages making up for massive fraction of this data? What's your first reaction to this? Is there a reaction? Yeah.
I'm unsure if the mass quantity just means that there's a lot more web pages out there than we might think, or maybe it's just this idea that, you know, with it being on the web, it's a lot easier to access.
Yeah, definitely.
Especially.
Yeah, so yes, both of these are true. There is more web data and it's just out there. So you can take it if you have a crawler. But my question was more, how do you feel about the capabilities of your language model being conditioned on learning knowledge that's mostly from the web?
Seems a bit iffy.
Yeah, iffy is a great word here, right? So a lot of things can go wrong. We are all, unfortunately, familiar with the good and bad sides of the internet. So the fact that there is a lot of web pages here raises some concerns. First thing we have talked about is how diverse this data is. We have lower quality, higher quality, we have code, we have a natural language, and so on. Another thing that's important for pre-training data is scale. The reason why we need a lot of data is because we are trying to learn general patterns, right? So more data you see, the more capacity the model has to learn about the world, right? So scale is important. Here in this little corner, I have left how many tokens have been used for various models. So BERT, which was released in 2018, used about 3.3 billion words. Words is not really tokens, right? So you can increase that by 10, let's say, that's generous. So it's maybe 30 billion tokens. GPT-3, which was released in 2020, demo, if not the weights, who had 300 billion tokens. Llama 2, which was released about 2 years ago, I believe, had 2 trillion. So you see the trends, right? Like more and more tokens are being in the pre-training data. And what I know anecdotally is that there is still more data than there is GPU compute. So basically, you get some budget for your compute. Rarely company has access to the GPUs like they physically own them. Rather, they borrow them for a certain period of time. So maybe you get GPU hours worth of 6 months. So you train your model for 6 months, and maybe you still haven't used all of the data. So we typically in the field will say that all of the pre-trained models are under-trained. Yeah.
I haven't really looked into this too much, but I've heard that we're kind of reaching like a scaling limit with our number of tokens that were presented for training. Do you have any comments on that? Is that true, or are we kind of like maxing out our transformers right now and going up to like 20 trillion tokens, I guess, is
Yeah.
that would make a huge difference? Do we
Yeah,
expect?
I think, I would say that we are definitely reaching the point of, what we can learn from more data, right? So, even if we had more tokens, what would we actually learn from it? Would it be this outbreaking difference? Likely no. And you kind of see that with the difference between GPT 4.0 and GPT 5 was somewhat, smaller than we have seen, previously. The big changes we want to see are with the type of data which is much rarer on the internet, right? So think about like simulation data of some robotics problem or things like that, right? That's not going to flow from the internet. So as long as it's not on the internet, they're going to have a harder time, handling that kind of phenomena, and that's something we are definitely see. So this is where this generation of data comes into a play, but let's hold on to this discussion of synthetic data until we come to another stage of LLM development called instruction fine-tuning, where we do use synthetic data. We don't use synthetic data for pre-training. So not to confuse everyone, we're going to talk about synthetic data, but not just yet. We are not using synthetic data here. Okay, now I told you that we need lots of tokens, but how many is a reasonable question. And this connects to the idea we call scaling laws. If you're a developer, you work for, I don't know, Gemini team, and you are responsible for pre-training, your employer will tell you, hey, we have this many GPU hours, train the best pre-trained model you have. So you know how much GPUs you have, and you count them in GPU hours. Now you need to choose how many training tokens and what size of the model you want to know. One thing that I want you to remember here, that in 2020, when Kaplan et al. Had released these first scaling laws, they have said, okay, you need this many tokens if you want to have a model of this size. And later, Hoffman et al. From Google DeepMind, they have released another scaling law. Basically, they said that these 2020 estimates were wrong, and then you need way less tokens that Kaplan et al. Had suggested. So I will read this out loud. They say specifically, given a 10 times increase computational budget, they, meaning Hoffman et al., meaning Kaplan et al., because we are reading what Hoffman et al. Have written, they suggest that the size of the model should increase about 5 times, while the number of training tokens should increase 2 times. Instead, we find that the model size and the number of training tokens should be scaled in equal proportions. And what they showed is, we all knew that GPT-3 model has 175 billion parameters. They have found that you can increase the model size drastically and train it with the same number of tokens and get the same performance. And that was hugely important. They have shown that you don't have to have such an enormous pre-trained models to have capabilities of a GPT-3 pre-trained model. It was a very, very important finding. But to this date, people will use these scaling laws coming from Hoffman et al. They, in this paper, released but mentioned a model that they trained using this law called chinchilla. So people will just refer to this as chinchilla laws. I know this field is so weird with like llamas and chinchillas and whatnot. It's, makes no sense, but it is what it is. So we call these laws chinchilla laws. And then if you read like more recent pre-trained models like Llama 3, you will see that there are still, these scaling laws are still used. People are still discussing them, to be honest. So, take them with still a grain of salt. But if you need to make a choice today, you will likely follow what they have done. Later, we will briefly mention something called test time scaling laws. That's a different kind of law. Hold on to thinking about that because we are not ready to talk about it yet. Okay, so now we have chosen some pre-training data. We have chosen certain number of tokens. now we need to filter that data. We can't just use it as it is because we have just said that using it on the data iffy to say at best, right? So there is a lot of noise and spam that's on the data. And I'm going to share, last time I was teaching this course, Kylo, this research scientist from AI2 gave us a presentation, which is available on YouTube, so you can check it out. But I will play a part of his talk that talks about how this noisiness can be problematic. So,
like, why is it important to have the data when you want to study these models?
do you hear this? Okay. How about you guys at the back row? So. Let me just try something. I see here I have a speaker is on mute. What if I am muted? No, it's not really. Okay, I will play it, and then if you don't hear it, let me know, and then I can repeat what Kyle has said.
And Dolma is the data set that I've been curating with my team. I'm going to give you a story, and the story is the microwave gang story to motivate why you should care about data. So these are logs from a typical pre-training run. When you do your pre-training, usually the models will your node might crash, you might have to spin it up again. That's why there's a whole bunch of these, but technically this is just the same pre-training run continuing, and this is a plot of the loss. And as you expect, the loss is going down over time as you train on more data. So this seems like good, but what are all these spikes? The spikes are the heart of the story of this microwave gang story, loss spikes. What does this have to do with microwaves? Well, if you actually inspect what's going on each time the loss spikes up, which is bad behavior, you'll notice that some of the data looks like this. And so one of those batches, actually the green one back here, if you actually go in to look at the data that caused the loss to go up really high, we found documents which are just Reddit posts from people in the subreddit, where in this subreddit, the rules are you can only post and then people can reply with beep. So it's like a microwave. But like this causes extremely weird behavior when you're training a model. And so a lot of these types of strange sequences, strange data elements can cause instability in your training run, which can destroy your entire run. Here's some more examples of bad data. Bad data can cause you partway through training, your training loss just starts going up. This isn't development loss, this is training loss. Can just start going up and it's irrecoverable. You can try different types of interventions, but as long as you're still training with that data, the loss will just keep going up eventually, and you might discover this very late in your training. Here's another example of a model that under previous configurations of the data and the training and the modeling code, it was doing well on this benchmark called MMLU. But for some reason, this blue run, it just could not figure out how to do this task, no matter how much you trained it. And we figured out in the data it's because we accidentally removed one type of sentence periodically, like as a bug in our data set, and it completely destroyed this training run. So you really need to care about the data because training runs are expensive. So this is how much it costs to pre-train one of these models. H100 is a GPU, costs about, let's say, $3 an hour these days. To train a 1 billion parameter model or 7 billion parameter model, up to the number of tokens worth of training that people are expecting these days, a failed training run because of one bug in how you process the data can cost you $100,000, $200,000, $500,000. For much larger models, they can take $6 million before you identify the issue. So these training runs, as a result of failed data, are extremely costly. Okay, so
remember when I said last lecture whether you want to be in a pre-training team? Yeah, so who knows? This is what I meant. Yeah, it's not an easy job. Okay, so the point here was that there is a lot of weird stuff on the internet, right? I mean, I have no idea why this subreddit exists. Who goes home and is like, I'm gonna write some on the internet, I'm gonna respond with beep beep. I can't imagine. But these things exist, and as Kyle had mentioned, this can have dire consequences for training, and training is expensive. The whole lecture is on YouTube, so I really encourage you to take a look. But we are going to go over some other problems today. So noise and spam is problematic, but also is bias and toxicity, right? So when we talked about word embeddings, this were the first time we talked about various societal biases that are very well represented on the internet, and how models, first of all, can learn to repeat very hateful things. So yesterday, maybe you were at Christian's guest talk, and he has shown you kind of things that toxic talk that emerges even in more civilized places like Wikipedia editing. Elsewhere on the internet, even worse, and we don't want our models to just repeat these things, right? And later we are going to talk about alignment and how we can prevent that, but in general, it's better that our pre-training data maybe doesn't have lots of those to start with. However, there are some contra-intuitive ideas here related to filtering. You might say, well, let's just find out all the toxic data, all the problematic data, and remove it. And this could have issues. One issue that this researcher had noticed is that if you fully remove toxic data from pre-training data, the model basically loses the ability to recognize what the toxic data is, kind of the concept of toxicity. And because it doesn't really kind of capture that anymore, it's really bad at then reducing toxic generation. Basically, it doesn't know this is toxic and I should not do it, so it doesn't do it. If you remove it, it has this concept, so it will be repeated more often if there is some of that toxic data present. So, you know, counterintuitive, but fully removing this data can lose ability, the model can lose ability that we wanted to have. Then in our own paper, we were looking into how people have approached this filtering. And I think I already mentioned this, how they have created this lists of forbidden words. And some of these words were completely normal words in queer community. And by doing filtering those kinds of documents with those words, you have erased any kind of voice and representation of that community, which is bad. And then maybe the most serious of all of this is this filtering to this day is being done by people. And people who have done this have reported extremely hard effects on their mental health by seeing a lot of really, really bad content on this pre-training data. So just the fact that we want to train this model to better the humanity, because now we have chatbots and we can do a lot of that, we shouldn't do that by harming people who are developing the data in that process. Related, I didn't mention it here, but it has been shown that these companies will hire refugees in refugee camps with, conditions of living that were just unimaginable to us that live here and have, high quality lives. And then this idea that someone is, producing this data that you can then train the model that all of us can use is also something to think about. Or typically the annotators are hired in places which have a lower hourly salary, like OpenAI has created its data to workers in Kenya and paid something like $1 per hour. And people were saying, well, we have such an immense budget, like why wouldn't you pay these people more appropriately? So yeah, bias and toxicities in data and how we filter, should we filter, is a big question. Then, of course, we all know that there is a lot of misinformation on the internet, and we also don't want others to repeat all that information. There is this benchmark, Truthful QA. Part of it is to see how often the models will say conspiracy theories, such as Earth is flat, for example. They will say it because of presence of such data on the internet. And also later when we talk about misalignment, we're going to talk about how byproduct of alignment is also this idea of psychopathy, that the models are agreeing with what we are saying to kind of make us feel better. Then you know that these language models, if you have China and mountain languages other than English, they work in English, in other languages as well, right? But to have that capability, you need to create pre-training data that has other languages, right? And if we take, that's a benefit of taking a snapshot of the internet. The internet has not only English, but other languages. However, issue is that English is still quite dominant. And actually, I will come to this, but let me come here. So this study, I don't know all the details of the study, but it claims that that vast majority of the internet is actually written in English. However, 3 out of 5 users of the internet in the world are actually unable to understand English. So that means that 75% of internet users rely on translation technology to be able to understand vast majority of the internet content. Now, to have a good translation tool, that means that you have that ability to translate to the target language, where the fact is that 80% of languages have no corpus for NLP modeling. And this is not, I'm not even talking about labeled data. There is not even unlabeled data out there. So sure, by scraping the internet, we get data in multiple languages, but it's still going to be predominantly English. This is a problem because according to this standard of language identification, there are over 7,000 languages in the world. And I looked a little bit into, I hovered over Croatia to see what kind of languages they say they are there. I think they are maybe overestimating some of like languages. I think for them, they have a notion that's not just linguistic language, but also social, socially political, which can make something that would be in a dialect that would say it's a language. But nevertheless, there is a lot of languages, even if some of these are dialects. So here are roughly 500 languages are institutional, which means that they are sustained by these institutions and governments. Over 3,500 are what's called stable languages. They are not, sustained by formal institution, but they are taught to children at home. So, for example, I have a very particular dialect in Croatian that I'm taught at home, but at school I would speak a more standardized version. And then the rest of the languages are endangered, meaning they are no longer the norm for children to learn and use the language at home, and many people think that's problematic. I took these slides from my Trey, who wanted to make a point that this one black line here is English in this big pie of languages. So another thing we wanted to emphasize is how languages differ. Like, why wouldn't just learning everything from English and a little bit of other target language data enable you amazing capabilities in target languages? First of all, is script. We are not writing all languages in Latin. We have many other scripts here in the NLP lab. I have no idea how this started, but our students started to ask everyone to write the word duck in whatever language they know. So now we have a whiteboard sacrificed to writing a duck, but it's at least useful to show various ways you can write the same word in different languages in different scripts. Different languages will have different word order. So I think most of us here are used to subject verb object order, but other languages like Hindi and Filipino won't have subject verb object order. And then there is semantic variation. So here, word data in Farsi means door, where it means puro in Gujarati. And similarly, this other word means education in Hindi, while it means punishment in Gujarati, which are quite the opposite. I would say, maybe you disagree at this point of the semester, but I would say education is a more like abstract positive word for me, and punishment is more like a concrete negative word. see some doubts there. I don't speak these languages, so you should talk to Matrey if he made some false claims. Okay, so and there are many more variations. So you can't have predominantly English and just a little bit of sprinkle of other data of other languages and think you will handle all this phenomenon. However, we are having attempts to collect these multilingual datasets. So the most prominent one is multilingual C4. C4 is a clean version of a snapshots of the internet from Common Crawl. And it supports 101 languages, so not many, and many out of those 7,000 or at least 500 stable ones we have seen. They have been detected using this language detector tool, and I will tell you that more, what you would say, low research languages, language detection tools are working really poorly for those. So even if you have this data in a low research language like Gujarati somewhere on the internet, having a detection tool which will detect that's Gujarati is not working well. So you have an extra layer of, of the problem of the finding the right data. Once you have a collection in multiple languages, you will again do your standard filtering, and then you can use this data to train a language model. One thing that's here important to handle is this idea of how to sample data from other languages. And you simply cannot, basically one idea could be, all right, I'm going to have as many data points in every language such that I treat them all equally. Well, look at how little data is there here, right? If we have chosen to strip every language data to that size, we will end up with way less data than we actually have. So the idea is that we are going to sample the data of lower resource languages a little bit more. So they are not going to be seen only once, as we typically see English, only one data point once. However, you want to be careful with how you sample the data from other languages. If you oversample them, meaning the model sees them too many times, we will have the problem of overfitting and memorization. If you don't see them enough, then you won't learn that language. So typically when people create multilingual pre-training data, they are taking care of how to sample data from different languages. Okay, and more recently, there is a bigger pre-trained language model, which has and supports 500 languages, so probably most of these stable languages. And they have also, I won't go into this, what they call chunk level filters, kind of to see whether, at the level of chunk of the pre-training data, things are clean, as well as a corpus level filtering. Okay, so there is some pre-training data, but today we can handle 500 of them, which maybe handles all the stable languages, but most of what we learn at home and not through institutions is not handled as of now. And that's experience I have with using ChatGPT in Croatian, for example. It's extremely formal and standardized and somewhat weird. I think having a conversation in my own dialect would be probably, I didn't try it, I should, but I suspect it won't work as nicely. Okay, let's wrap with other issues. Another issue is that now we serve the internet, people put everything on the internet, so private information is now part of the data. And what people have shown is that you can find a way to prompt these language models, and they will give you private information about people, which is not what we want. So we need to take care of private data, and typically we'll do some kind of filtering to remove any PII information. But it's something to keep an extra, focus on if you ever think about doing applications such as those in realm of medicine, where you don't want to release the information about your patient, for example. So if you ever think about working in those application areas, you have to remember this problem. This is why typically, if you do this ethically, you would have your model, local model, on the same GPUs where your data is. So everything is local and there is no chance for the leakage. Or if there is, you can remove everything and people can't use it. Okay, now similarly, copyright and intellectual property, right? So people release stuff on the internet, maybe they release their book, and now suddenly that contents of that book are, used without proper attribution. And you have probably seen many lawsuits recently against OpenAI and Anthropic for comedians, book writers, and other people who have sued them for using their copyrighted materials without any attribution. So I'm going to go a little bit over this. Why was it ever okay to use this data? How many of you have heard about fair use? Can you raise your hand? Great. So most of you have heard it. I will just repeat it for those who don't. No, there were other legal cases, and byproduct of those legal cases was that if you want to use data for purposes of text and data mining, this is allowed. You can use this data, and you can use it as long as whatever you are producing with that data would not take away the jobs of people who have created that data. And now immediately you can see the difference before technologies such as search engine and ChatGPT, right? Now, ChatGPT can produce illustrations that can replace, people who do simple illustrations or simple stories, right? So now there is a debate whether, is this fair use, right? Like, is this what I put in bold, is it violated? I also want to mention this term contractual override, which you probably haven't heard about. So although fair use says you can use this data and you are allowed as long as you don't take it out of the person who has created the data, still somehow in the practice, publishers may so-called contract around and require libraries to negotiate what are lawful activities. So the library can use this data and doesn't need anyone's permission. The publishers can still, this article terms, contract around and require compensation for that. So there are very weird practices that are happening around this. Now, not every LLM developer wants to steal data and steal a job. People want to create these models ethically, and they are wondering how to do this in the best way possible. The fact is that if using pre-training, internet data is no longer fair use, the companies and nonprofits that are going to suffer are those that can't, they don't have means to contract around and buy licenses for all this data. OpenAI, Anthropic, Google, they will be able to buy licenses and buy data, and they will build tools that there will be proprietary tools that they can then, ask compensation for using. Whereas open community can actually use the data, create the tools, and give it back to the community. So it's a really weird situation. And there are efforts how to pre-train on a permissive data and use the copyright data more like a database you retrieve from people. People are thinking about that too. Okay, we are by the end of the lecture, so I will just mention quickly two other issues. One is data contamination. Doing machine learning research has become notoriously hard now. Our first principle, don't train on your test data, is no longer easy to guarantee. So people have put their test sets on the GitHub, right? And now that GitHub is part of pre-training data. It's just a mess, right? So we have cases where we could confirm that the test set is in the training data. If you read GPT-3 paper, they actually themselves say that they have trained on all the test data accidentally and then couldn't rerun GPT-3 training because that's, as we have heard from Kyle, incredibly expensive experiment. So things happen, and data contamination is a huge issue. And then lesser issue, but formatting issues such as HTML artifacts and parsing errors, that's still something that we need to take care of. But regardless of this noise, these models have been able to learn. So I think that is not a huge issue. Okay, there are some few other practicalities I wanted to mention, but I can mention those some other time. All right, let's stop here and then let's start talking about question answering next time.